So now that we have an idea on what are the types of reactions, let's look at some of the at a question that can be asked regarding them. So it says calculate the standard enthalpy change of reaction for. This is the equation which they've given us, and this is the data. This is the value of data that they have given. So they've given us the compound and their enthalpy change of formation. For now, it's not important to note this down, but it's always good to know what type of information they've given you. So, right here, they've given us standard enthalpy of formation data, but that will come of importance later on. So, now let's see what the question has asked us to do. So, standard enthalpy of, in order to understand what they want, this is the form of standard enthalpy of reaction. Reaction we know is with R, and from our definitions we know that standard enthalpy of reaction can be defined as this formula. So let's apply this formula. So this is our reactant side, and this is our product side. So we're going to calculate these very separately. So now we have a standard enthalpy change of formation of CS2 plus 4 times the standard enthalpy change of NOCl, and this forms our, oh, that didn't come out well. This forms our sum of standard enthalpy change from the product side and our of our reactant side, sorry, and this will be our product side. So we're going to form this the same way, CCl4 plus, don't forget the number that's right in front because that's very important for these type of calculations. SO2 plus, I'm going to have to do this down because I don't have space, N2. So now can we see, so we have CS2, we have the data for that. Let me move on top. We have for CS2, and we also have the data for NOCl. We have the data for CCl4. We have the data for SO2, but we don't have the data for N2. The reason is because you cannot form, nitrogen is already an element. You cannot form nitrogen again. So its standard enthalpy of formation will be zero because you cannot form an element. It already exists. So now let's plug in all the information we know. So from the table, we know CS2 is 88 plus 4 times NOCl, which is 53. And this altogether gives us 300. And on our reactant side, we're going to plug in negative 139 for CCl4 plus 2 times SO2, which is negative 296, plus 2 times 0, because elements cannot be formed again. And so so finally this is going to, when we calculate it, it's going to give us negative 731. Now from our equation, don't forget the values, kg mole. And so now we're going to plug it into our equation. So we know it's the reactants which is on that side minus the minus the enthalpy change of products. So now if minus and plus becomes a minus, therefore we have to add this, which gives us negative 1331 kilojoules per mole. And this is how you would do a calculation regarding standard enthalpy change of reaction. And this is in the very simple form. But now we are going to move into Hess's law. And we can see more ways on how to calculate the standard enthalpy change of reaction when they give you different values. So let me write the title. So now Hess was um, Hess was a Russian chemist, and he came up with a chemical version of principle of conversion of energy. So the conservation of energy is that energy can never be destroyed; it can only be converted. And so what has came up with is the law that he found out is the total enthalpy change for a reaction is independent of the route taken. So let's first understand by what that definition means. If I want to make a reaction which is A plus B gives us C, if um, if another set of reactants, say suppose D plus E, also gives us C, we can use and A plus B can be formed from D plus E, and therefore we can say D plus E can also form C. So to better understand this, we're going to use examples, but it's best to know this is how the Hess cycle is going to be. So the first type of Hess cycle we're going to take a look at is standard enthalpy change of formation. That means when you have a standard enthalpy change of formation type data given to you. So let's take an example. I'm going to write it in green. So I'm going to take the example that is on page 8 of unit 2 from our chemistry reader or booklet. Um, in there it is CH4 plus 2O2 gives CO2 plus H2O, and we and carbon and 2H2 will also give that. So how do we form the bottom line? Let me erase this and show you step by step on how to form the lower line. So because this is standard enthalpy change of formation, remember that standard enthalpy change of formation is when a compound is made up of its elements. So this is the compound that we are looking at because it burns with oxygen. So this is the main compound we are looking at, and it's made up of carbon and hydrogen. So it is C plus H2, and remember these elements should be in their standard states. So carbon is as carbon in its standard state, and hydrogen is H2 in its standard state. But see that it's not balanced. So we have to add a 2 in front of the H because so then we will have 4 hydrogens here and 4 hydrogens here. And in standard enthalpy change of formation, our arrows are always going to be pointed upwards, no matter what the reactions are. And so This is how you form the bottom line and how you form the top line. This is going to be our x because that's what they've asked for. They have asked calculate the enthalpy change for the reaction. So this is the reaction. So the best way to solve this is by writing the data on the arrows. So for this I'm going to write, because it's standard enthalpy change of formation, we're going to write this symbol CH4 plus, and we have oxygen as well, so it's 2O2, and this is on this arrow. For this arrow we have CO2 plus H2O. We've got 2 H2O here, so we're going to put a 2 in front of this. So now we've got our data for the arrows. Now let's find a particular direction to do it in. So we have a clockwise and an anti-clockwise direction. So we can see that this arrow and this arrow are going in a clockwise direction. So it's going through this way. Therefore, we'll call it delta H1. And this one particular arrow is going in this direction. So we'll call that delta H2. So now let's from Hess's law we know delta H1 is equal to delta H2, because he said um, from the Hess's law, it stated that the total enthalpy change for a reaction is independent of the route taken. Therefore, delta H1 is equal to delta H2, although they are completely different paths. So, delta H1 has these values plus an x. So let's put that in. So we've got delta HF theta CH4 plus 2 times HF theta O2 is equal to, oh, we've got plus x because this arrow is also included, is equal to, now we have this arrow, this is the information that we have. So you can see why it's useful to write the information on this side. Theta H2O. So now let us plug in the values from what is given in the uh, data table. So for CH4 it's negative 74.9 plus 2 times O2. Since oxygen cannot be formed, it will be 0 plus an X. For CO2 we've got negative 394 plus 2 times H2O is negative 286. And by solving this side, we got negative 74.9 plus x. And using math, we've got this side as negative, we've got this side as negative 966. And therefore, bringing this to the other side, it'll become plus, and therefore your x will be negative 891, 91.1 kilojoules per mole. And this is how you would do a calculation of a Hess cycle in standard enthalpy change of formation. Next, let's look at how to calculate the standard enthalpy change of combustion.